For centuries, the traditional educational paradigm has operated like an industrial assembly line. It treats students as passive storage devices, human hard drives expected to receive, store, and eventually regurgitate uniform packets of information. This model made sense when information was scarce. In the 20th century, academic research was defined by physical and logistical friction. An enormous amount of a student's time was spent merely locating the physical existence of data. Extracting and verifying that data required labor-intensive manual processes. By the time a researcher finished scanning microfiche and transcribing quotes by hand, a significant portion of their cognitive energy was already spent on pure logistics. Today, algorithmic retrieval happens in milliseconds. A machine can synthesize millions of documents and identify complex patterns faster than a human can walk into a library. Relying on the human brain merely to store and retrieve data is functionally obsolete, but applying this sudden, frictionless speed to the old rote memorization model is dangerous. If a student uses an algorithm to simply bypass the work of finding an answer, they bypass the learning process. The result is surface-level output with zero deep cognitive engagement. Consider the Tamiri thought experiment. If you are asked to study and define the word Tamiri, a completely fabricated term, your brain has no real-world context to attach it to. You can memorize the spelling, but without lived experience or contextual inquiry, the information evaporates. Using generative AI to accelerate a pipeline focused on injecting facts guarantees cognitive atrophy. To extract actual value, educators must move away from memorizing answers and toward the active practice of iterative inquiry. A persistent anxiety among faculty is that integrating AI means inviting an independent, autonomous substitute for human teaching into the classroom. To understand why this is a misconception, we have to look at how AI architectures are classified. This graphic outlines the distinction. On the left is strong generative AI, an autonomous system imitating human thought. The right column shows the reality today, weak generative AI. It functions as an interactive co-author, executing tasks under human direction. Modern educational technology relies entirely on this weak, targeted architecture. Because these systems lack internal intent, the human-in-the-loop protocol is the structural foundation that makes the technology safe for academic use. This flowchart tracks that critical transition. Moving from the theoretical concept of an autonomous system to the practical deployment of a targeted tool changes its role. It becomes a catalyst designed to amplify human capabilities. Generative AI is not an independent academic subject or a teacher replacement. It is a cognitive instrument that requires structured pedagogical management to function. At the student level, this integration is currently defined by a sharp friction between academic integrity and daily use. This data visualization isolates the primary concerns. Nearly 60% of surveyed students express anxiety about plagiarism and the loss of originality. Simultaneously, over 52% point to the risk of hallucinations, where the AI generates confident but completely fabricated facts. Yet, despite these high levels of mistrust, over 80% of these same students utilize generative tools on a daily basis. Efficiency often overrides their ethical concerns. The architecture of academic ethics shown here manages this friction. By mandating transparency and keeping a human in the loop, institutions can integrate AI into grading rubrics, shifting it from a tool for cheating into an authorized research assistant. Moving beyond simple policy memos, educators need a specific structural framework to manage the interplay of technology and ethics in a live classroom. The TPACK model is essential. An educator must synchronize technological knowledge, their baseline AI literacy, with content knowledge, covering ethics and privacy. The system locks together when pedagogical strategies engage the bottom gear, connecting skills to active learning designs. Faculty readiness is the critical bottleneck. Without the TPACK framework, institutional transparency policies are difficult to translate into practical classroom instruction. Down at the student execution level, unstructured interactions create a different kind of failure. Typing casual requests into a language model produces shallow, generic outputs. To extract rigorous academic value, prompt creation must move from a chat interface into an exact engineering process using the RTRO microframework. Using this workflow, the process begins by assigning a role and a task to anchor the machine's context. The student then sets hard requirements, like eliminating jargon, and defines the exact output format, such as a data table. This entire workflow is iterative. The algorithm's initial response is treated as a raw draft that demands critical review and refinement by the human operator. The RTRO framework shifts the student's mental energy away from the manual assembly of sentences. Instead, it focuses their cognitive load on logic, constraint setting, and critical evaluation. Even with precise micro-frameworks like RTRO, learning will remain fragmented if these interactions aren't embedded into a broader curriculum design. The architectural solution for integrating AI into a semester-long curriculum is the Live PBL DEEP methodology. This diagram maps the project pipeline. Through the initial direction and education phases, AI acts as a brainstorming partner. Moving through the event phase, it facilitates real-world application across cultural barriers, culminating in the project phase driven by algorithmic feedback loops. Notice how the utility of the AI shapeshifts across this timeline. As shown here, the algorithm morphs from an idea-generating research assistant to a student mentor and a tool for deep content personalization. The Live PBL DEEP method transforms generative systems. They become structured, continuous partners in a student's long-term academic development. Structural efficiency only accounts for a fraction of this technology's potential. Its highest value is realized when it acts as an equalizer, removing barriers for marginalized learners. A case study involving special educational needs students in Hong Kong provides a clear demonstration of this capability. This workflow charts the challenge. The red barrier box outlines how physical and cognitive limitations have historically blocked these students from participating fully in creative tasks, particularly those requiring fine motor skills. By introducing text-to-image tools, the technology bypasses these motor limitations, allowing a student to translate their intent into a high-fidelity visual output. As noted in the green box, removing constraints drives a sharp increase in student engagement, self-confidence, and digital literacy. A correctly architected system provides true creative enfranchisement. Here, AI's highest value is measured by the new capabilities it grants to the learner. We have arrived at a definitive inflection point in education. Because machines now possess instantaneous access to factual answers, measuring intelligence through rote memory is an obsolete metric. This graphic maps the architecture of a modern educational ecosystem. It relies on a balance between the student, the technological instrument, and the human mentor. The top node redefines the student as the active driver of inquiry, engaging cognitively and emotionally, rather than acting as a passive receiver. The mentor node redefines the teacher. Leveraging frameworks like TPACK, educators provide the empathetic oversight and pedagogical design that algorithms cannot replicate. The modern university now moves away from testing recall. The focus shifts to cultivating a student's capacity to formulate the specific questions that drive discovery. When guided by human intent, these tools increase the complexity and depth of what a single researcher can produce.